Hello and welcome to Part 3 of Construction Scheduling, Creating the Network Schedule, a Tech Training LLC presentation. In this segment, we're going to build the construction schedule, and we're going to do the calculations for forward pass, backward pass, free float, total float, and lag times. So, without further ado, let's go ahead and get started. So far in this presentation, we've covered the difference between planning and scheduling, early innovators of scheduling, the advent of computerized scheduling, types of schedules, the work breakdown structure, and defining activity durations, all of which is required to develop the network schedule. In this segment, we are going to actually create the construction schedule. Now, our schedule will be based upon activities and their immediate preceding activity, or their IPA. The precedent schedule is the most commonly used network schedule. In fact, most scheduling software programs require the use of precedent activity input. As you've already seen in precedent diagrams, scheduling activities are typically represented by nodes in the form of rectangles, circles, triangles, and squares. Now these activities are placed in the schedule in diagram form and read left to right. The nodes have varying information in them. As an example, most will have early start, early finish, late start, and late finish. These items will also be represented by dates, or in some cases simply numbers, which represent working days or calendar days. Now the various lines in the diagram are not meaningless. They represent the links between activities. These lines represent the interdependencies that one activity has upon another. Links are also viewed left to right to indicate the relationship, meaning the left side of the link is the beginning of the link line and the right side is the end of the link line, which connects the two activities. This also means, in this case, the link line represents a finish to start relationship between the two activities. In other words, B cannot start until activity A is finished, activity C cannot start until activity B is finished, and so on. The finish to start relationship is the relationship that most of us are familiar with. It is logical and therefore makes sense in the construction industry. In a finish to start relationship, once an activity is finished, its succeeding activity can begin. By putting everything into a finish to start relationship, we can simplify relationships and the schedule itself. But it is worth noting that computer software can quickly calculate any activity relationships. It is also worth noting that the link lines between activities consume no resources, not even time, unless, of course, we want them to. As an example, in this typical finish to start relationship, the link lines consume no time. Our first activity is to place the concrete. The next activity is curing the concrete, which takes 28 days. And then the last activity is stripping the forms, which is going to take 2 days. But since the activity of curing the concrete consumes no manual resources, only time, we may want to depict the same schedule as seen here, using the link lines to indicate the delay between placing the concrete and stripping the forms. Once again, these are finish to start relationships. In other words, an activity cannot begin until its preceding activity has been finished. So now let's take a look at some other types of activity relationships. One type of activity relationship that may be encountered in a construction schedule is the finish-to-finish relationship. In this type of relationship, two activities must be completed at the same time. Here we see an example of the finish-to-finish activity relationship when setting a fence post. A simple task which requires the finish-to-finish relationship. Here we see the second activity, setting the fence post, has a finish-to-start relationship with digging the hole for the fence post. We can't set the fence post until the hole has been dug. Now the next activity is positioning the post. And again, positioning the post has a finish-to-start relationship with setting the fence post. We cannot position the post until we've set it into the hole. But note that positioning the post has a finish-to-finish relationship with backfilling the hole. These two activities must finish at the same time. Now next is a start-to-start relationship. In a start-to-start relationship, two activities must begin at the same time. As an example, the placing of a concrete sidewalk. As the concrete is being placed, the finishers are screeding the concrete directly behind the placement. Therefore, the placement of the concrete and the screeding of the concrete must start at essentially the same time. Our next activity relationship is start to finish, not to be confused with finish to start. With this type of an activity relationship, one activity cannot be finished until a previous activity has been started. As an example, if we take a look at our concrete sidewalk, we may get delayed if we went with the traditional finish to start relationship. As seen here, it is suggested that the concrete cannot be ordered until the formwork is completed. Ordering of the concrete is not dependent upon the completion of the forms, and since most ready-mix producers do want some lead time on the concrete. An easy way to depict this is as shown here, and what this schedule is showing is that the forms have to be completed before the concrete can be placed. Therefore, setting the forms and placing the concrete is a finish-to-start relationship. Again, the forms have to be completed before the concrete can be placed. But the activity of ordering the concrete and the activity of placing the concrete is a start-to-finish relationship with a 5-day delay in between. In other words, ordering the concrete must be started or finished 5 days in advance of placing the concrete. And again, the placing of the concrete and the screeding of the concrete have a start-to-start relationship. So as you can see, activity relationships are extremely important to the construction schedule. They can be confusing. But once again, this is the importance of planning out the activities as discussed in previous segments of this course. Understanding the relationships between activities and defining activities are critical steps before beginning the construction schedule. Now, moving forward for the purposes of this presentation, all activities will be presented in the finish-to-start relationship. So now, before we get started, just a quick reminder of some of the general rules of scheduling. First, never confuse link lines with activities. Link lines can have time associated with them, but they are not activities. Nodes can be almost any type of character. They can be circles, squares, rectangles, etc. We will be using rectangles here, but don't think that you'll always see rectangles in the field. Create and use an IPA table, and that is not a table that's filled with beer. It is a table with immediate preceding activities. We will be showing you the one that we'll be using for our schedule in a moment. And lastly, after completing your IPA table, draw out a rough diagram schedule. This will help you quickly identify if you have missed any activities. So now, let's go ahead and begin our schedule by taking a look at the IPA table. This is our IPA table. It shows all of our activities and its immediate preceding activity or activities. As you can see, Activity A has no preceding activity as it is the first activity in our project. Activity B cannot begin until Activity A is complete, and the same is true for Activity C. And as you can see, the rest of the table is filled in. So now, let's move on to the calculations that we're going to be performing in our schedule. Now the calculations that we'll be performing, the forward pass, the backward pass, free float, total float, etc., have meaning. The goals of these calculations is to find the times that each activity is going to begin. We're also going to find the critical activities throughout the project. And we're also going to find out how long is this project going to take. Now, once all of the durations have been established, the job calculations can begin. And the job calculations are defined as the early start, or ES, early finish, EF, late start, LS, late finish, LF, free float, FF, total float, TF. Durations are typically listed as DUR, and finally we're going to assign resources to each activity. Now, one of the most important pieces of information that we're going to get from these calculations is we're going to be able to identify the critical path. Once again, the critical path is going to show us the activities that must be completed in order for the project to be completed on time. Now here are the equations for our schedule calculations. For the forward pass, we are going to take the early start plus the duration is going to equal the early finish of each activity. The backward pass is the late finish minus the duration is going to equal the late start. And total float equals the late start minus the early start. Now the reality is that there's many different ways to calculate the total float, not just late start minus early start. We can also take the late finish minus the early finish. We can also take the late finish minus the early start plus the duration. But for simplicity and to stay on one system of calculations, we are going to use the late start minus the early start. Now, once we're done with the backward pass, the forward pass, and the other calculations, we're also going to calculate lag time and free float. However, let's complete the other calculations first before we get into these calculations. These calculations are beneficial to the schedule, very beneficial, but we have to do the other calculations first. Now this is our schedule, and again it may look familiar to you because it is the schedule that we have been using throughout this course. But now we're going to actually fill it in by beginning with the forward pass. And again, the forward pass is going to tell us the shortest amount of time in which the project can be completed. Now in the upper left-hand corner of your screen, you see a rectangle, which is similar to the rectangles that we're using in our schedule, and this is simply the key to the boxes within the rectangle. So in the upper left-hand corner, you see ES, which is the early start, and right next to that is DUR, the duration of the activity, and then late start. In the next row, we see EF, which is the early finish, FF, free float, TF, total float, and LF, late finish, and below you see the resources. So as you can see, for activity A, it's going to take 1 day, and the resources are going to be 2 carpenters and 1 laborer. Now the first thing we're going to do is assign an early start to activity A. Activity A will be the only activity that we assign an early start to. The remaining early starts will be calculated from previous activities, which we'll go through in a moment. But here we're going to assign 1 as an early start, meaning that activity A begins on the first day. Now, to calculate the early finish of activity A, we simply take the early start of activity A plus the duration of activity A equals the early finish, or in this case, 1 plus 1 equals 2. So all we've done is steps 1 and 2, which you see here, and now we're going to move forward and calculate the early start and early finish of all the activities. This is the forward pass. So our next step is to calculate the early start times of activities B and C. The reason that we can calculate these early start times is because activity A is complete. The early start time of activity B is going to be 2, and the early start time of activity C is going to be 2. These early start times are coming from the early finish time of activity A. The early start time of any activity is going to be the early finish time of its preceding activity. The only exception will be when there's multiple preceding activities, which we'll encounter in a moment. But for now, we can calculate our early finish times for both activities B and C, which are 6 and 4 respectively. So we have now added step 3, which is determining the early start time of succeeding activities by determining the early finish times of the preceding activities. And now we can calculate the early start and early finish times of activities D, E, F, G, and H. Activity D and activity E are going to have early start times of 6, as this is the early finish time of activity B. And as you can see, activity D and E are dependent upon activity B. Activities F, G, and H are going to all have early start times of 4. Again, this is coming from the early finish time of its preceding activity, which is activity C. And we can now go ahead and add in our early finish times for each of these activities. So step 4 is simply a repeat of steps 2 and 3 as we move forward through the forward pass. Now the early start of activity J is obvious, it's 7, which is the early finish of activity D. But what about the early start of activity L? It does have 3 preceding activities, F, G, and H. Well, the early start of activity L should also be obvious. Activity L is dependent upon the completion of activities F, G, and H. And the last activity to be completed amongst F, G, and H is G at 8 days. So the early start for activity L is 8. And we can now move forward to activities K and activity M, which completes the forward pass. And by completing the forward pass, we now know that the earliest possible time to finish this project, again, providing everything goes smoothly, is 17 days. And now that we've completed the forward pass, we can complete the backward pass, which is going to tell us our late starts and our late finishes. And once again, late starts are going to tell us the latest time that an activity can begin and still finish on time, while the late finishes tells us the latest time that an activity can be completed without impacting the entire project schedule. Now we begin the backward pass with the last activity. And to determine the late start and the late finish of the last activity is quite simple. It is the early start and the early finish of the last activity. This only makes sense because if each activity stays on schedule or at least finishes before the late finish, then we should complete the entire project on time. So we have now completed step 5, which was assigning the late start and the late finish to the last activity. And again, the late start for the last activity is the early start of the last activity, while the late finish of the last activity is equal to the early finish of the last activity. But note, this is only true for the last activity. So the backward pass is done in a similar fashion as the forward pass. But here, the late start of the succeeding activity becomes the late finish of the preceding activity. So let's go ahead and take a look. So here, the late finish of activity K and the late finish of activity L will be 16. Again, this is coming from the late start of activity M, K and L's succeeding activity. Now to calculate the late start of activities K and L, we simply subtract the duration from the late finish. So here, the late start of activity K is going to be 10, and the late start of activity L is going to be 14. And now we can continue with the backward pass. The late finish of J is going to be 10, which is the late start of activity K. E is also a direct preceding activity of K, therefore its late finish is also going to be 10. While activities F, G, and H will all have late finishes of 14, which is coming from its succeeding activity, L. And we can now calculate the late start for all of these activities, again by simply subtracting the duration of the activity from that activity's late finish. And we can now fill in the late finish for activity D, which is 8, and its late start, which is going to be 7. Now, of course, we see that we have a similar problem as when we were doing the forward pass. Both activities B and C have more than one succeeding activity. Therefore, we have to determine which of the late starts will become the late finish for these activities. Well, again, I hope that the answer is obvious. When we faced this situation on the forward pass, we would always use the latest early finish going forward. But here, we're going to use the earliest late start. Therefore, the late finish of activity B will be 6, which is coming from activity E, and the late finish on activity C is going to be 10, which is coming from activity G. And we can now finish off our backward pass by bringing back the late start of activity B to become the late finish of activity A, and this is going to complete the backward pass. The backward pass tells us the latest time that an activity can start without impacting the activity, and the late finish tells us the latest time that an activity can finish without impacting the entire schedule. Now we can go ahead and calculate our total float. And to calculate total float, again, all we do is we subtract our early start from our late start or our early finish from our late finish. Now, total float, not to be confused with free float, is the amount of time that you have on an activity before it impacts the entire project schedule. As a general rule, you should do both calculations, early start from the late start and early finish from the late finish. And if you have a different result, then you probably have a problem. As an example, on activity M, the late start of 16 minus the early start of 16 equals 0, while the late finish of 17 minus the early finish of 17 also equals 0. Moving on to activity L, the late start of 14 minus the early start of 8 equals 6, and the late finish of 16 minus the early finish of 10 also equals 6. And we hope you can see how this works, so let's go ahead and fill in the total float for the remaining activities. And now that the total float has been calculated for all of the activities, we can now determine the critical path. The critical path is going to show us any activity that must be completed on time to complete the project on time. These are the activities which are considered critical. The critical path can be determined by following the schedule through any activity that has no total float. So in this example, our critical path would be activity A to activity B to activity E to activity K and to activity M. This is our critical path. Now we're still not done. We still have to calculate lag time and free float. But let's begin with lag time. Lag time is the amount of time between the early finish of an activity and the early start of a specific succeeding activity. It's calculated as the lag between two activities equals the early start of an activity minus the early finish of its preceding activity. Now lag does not have a place within the actual activity node, but instead is listed along the link lines. Also, when calculating lag times, you should begin with the last activity and move in a backward pass motion. So, as an example, the lag between activity M and activity K is 0. We get this from the early start of activity M, 16, minus the early finish of activity K, also 16, while the lag between activity M and activity L would be 6. Now, even though we did show the 0 lag time between two activities in the previous slide, that was for informational purposes only. Normally, if there is no lag time in between two activities, you will simply show nothing along the link line. So, if we fill in the rest of our lag times, we should have 1 day in between activities J and K, 1 day in between activities F and L, and 2 days in between activities H and L. In this schedule, we have no other lag times in between any other activities. Now you can imagine the importance of lag time when the schedule begins to get detracted by unforeseen conditions, such as bad weather or materials not being delivered and so on. But in a later segment of this course, we will be talking about the importance of lag time when it comes to crashing the schedule. So the last thing we just did was determine the lag time, and now we're going to take the final step in the schedule, which is determining the free float. Free float is the amount of float that you have on an activity before it impacts the next activity. This is not to be confused with total float, which is the amount of time you have on an activity before it impacts the entire schedule. Now, free float is determined by being equal to the smallest lag value of all the links which are going back to that specific activity. As an example, the free float of activity L would be 6, while the free float of activity K would be 0. And when we complete all of our free float times, our completed schedule should look like this. Now this is a fairly simple schedule, and the amount of free float is not particularly puzzling. But you can only imagine how on a large schedule with many activities, how free float could quickly become a very important resource. And speaking of resources, the one thing that is missing from this schedule is reality. Because the reality is, when we did this schedule, we did not consider resources. We assumed that we had all of the necessary resources to complete each and every task. In our next segment, Resource Allocation, we're going to be reviewing what to do when our resources suddenly become limited. But for now, let's review the steps of creating the network schedule. And here for your review are all of the steps to creating the network schedule. And ladies and gentlemen, this is going to conclude segment 3 of this construction scheduling course, Creating the Network Schedule, a Tech Training LLC presentation.